Hey everyone, I'm Mr. A and welcome back to part 2 of my quadrilateral family tree video. If you missed part 1, there's a link in the description so you can go back and catch that. In part 1 we talked about the beginning of the tree and we proved all of these properties for a parallelogram. Now we're going to continue imposing additional restrictions to get more specific quadrilaterals. So again, from the quadrilateral we imposed the initial restriction of one pair of parallel sides. That got us a trapezoid. Then we asked for a second pair of parallel sides. That got us a parallelogram. And lots of interesting properties pop up for a parallelogram. Now we've got a choice. There are two additional things that we could ask of our parallelogram. So if you think about what a parallelogram has, it's really only got two things to offer. It's got sides and it's got angles. We've already made opposite sides parallel, so we can't talk about parallel anymore, but we can talk about making those sides congruent. So one thing that we could ask, this blue arrow, could be asking for all sides to be congruent. In other words, ask this shape to be equilateral. The other restriction I could impose on my parallelogram is I could ask, this blue arrow could ask for all angles to be congruent. Right? So I could ask for all angles congruent, which is to say equiangular. So think about what those two restrictions would do to my parallelogram. If I take the parallelogram and I ask it to have all congruent angles, well, we already know that all the consecutive angles, say for example these two on the bottom, have to be supplementary. What would happen if I make supplementary angles also have to be congruent? What type of angle would they end up being? They'd end up being a right angle, wouldn't they? So if I take my parallelogram and ask for all congruent angles, what I end up with is a rectangle. It just straightens the shape out into our classic rectangle. On the other side, if I ask for all congruent sides, then what happens is the shape doesn't straighten out at all, but it's going to get stretched horizontally or vertically, and I'll end up with what we call a rhombus. So these two shapes are both still parallelograms. They're just more specific versions of a parallelogram. Let's take them one at a time. Over here with the rectangle, we have some new properties. Of course, we have the obvious property that all angles are congruent, right? So all congruent angles. You can also think about that as just being all right angles. Those are essentially the same property when you're talking about a quadrilateral. Right? So all congruent angles are all right angles. The other property we get that's kind of cool is that the diagonals are now congruent. Now this was not true for a parallelogram. In a parallelogram, you can have a long diagonal and a short diagonal. But in a rectangle, we only get one length for the diagonals. They're always going to be congruent. So let me go ahead and take a look at a rectangle and let's prove that before we go any further. So here I have a rectangle and in it I'm simply going to add the two diagonals. So AC and DB. All right, so we can construct those two diagonals and then let's talk about how we know they're congruent. So can you find a pair of triangles that if you knew were congruent would allow you to say that AC and DB are congruent? Can you find a pair of triangles in this picture that would let you say AC and DB are congruent? Well, it's got to be a pair of triangles that have AC and DB as sides, right? Otherwise you can't say anything about AC and DB. So one triangle maybe we could look at is this triangle ADC. Right? So that has AC as a side. And then for another triangle, let's pick one that has DB as a side. So maybe we look at DBC. Now those aren't the only two triangles you could use, but they're a perfectly nice set to try. So let's first talk about the fact that these triangles both have a right angle. So let me just go ahead and number those 1 and 2 to make life a little bit easier. Right? So these two angles here, 1 and 2, those are going to be congruent because in a rectangle all the angles are congruent. So we got angle 1 congruent to angle 2 because all angles congruent in a rectangle. What else do I know about those triangles? Well, they share this side, don't they, DC? That's literally the same side down there. So if they share that side, we can talk about having a reflexive down there on DC, and that'll give us a pair of sides in our triangles. What else? We're going to need one more thing to get those triangles congruent. So think about the properties that a rectangle has. Now, a rectangle is still a parallelogram, right? If we go back to our quad tree for a second here, a rectangle is sitting right underneath the parallelogram. It is a more specific type of parallelogram. that means it has all 6 properties that a parallelogram had. In particular, that means the opposite sides are going to be congruent. So if we pop back to our rectangle here, since I know opposite sides are congruent, that would let me say that AD is congruent to BC, right? So if I get AD congruent to BC, now I've got triangle congruence. Triangle ADC is congruent to triangle, let's see, BCD, and that's by side angle side. So what does that allow me to say? Well, since AC and DB are parts of those triangles, corresponding parts, I should say, that means that AC and DB are congruent by corresponding parts of congruent triangles. So there you go. We have the diagonals of the rectangle are congruent, and going back to our quadrilateral family tree here, we can go ahead and check that one off as being proven. Notice I didn't prove that all the angles are congruent because I don't need to. Why? That's the definition. That's how we got the rectangle. We asked for a parallelogram with all congruent angles. Now let's pop over to the rhombus. So on the rhombus, we asked for something else. We didn't worry about the angles. We asked for all the sides to be congruent. So we end up with this sort of tipped over square. And a rhombus, so of course, has the obvious property that all sides are congruent. It is equilateral, right? But we get 2 other pretty neat properties about the rhombus. They're both to do with the diagonals. So the diagonals of a rhombus bisect the angles, right? So that means if I put the diagonal in here, it's going to bisect the angle there and there. And the other thing that diagonals do is they are perpendicular to each other. The diagonals are perpendicular. So the all sides congruent, that's the definition. I don't need to prove that one, but I will need to prove these 2 facts about the diagonals. So let's go ahead and prove that the diagonals of a rhombus are perpendicular and bisect the angles. We have our rhombus ABCD here, and let's go ahead and mark all 4 sides congruent so that we know that we're dealing with a rhombus. Let's also go ahead and construct the 2 diagonals since we're trying to prove that the diagonals are perpendicular and that they bisect the angles. So we're going to need those diagonals. So let's see. So we'll construct AC and DB, right? So in our rhombus ABCD here. Now what are we going to need to prove in order to prove that the diagonals are perpendicular and that they bisect the angles? So bisecting angles is pretty straightforward. We have to prove that these angles are congruent, right? These 2 here, these 2 here, these 2 here, these 2 here. To prove that they're perpendicular, we need to show that some of these angles in here are right angles. So let's focus on a couple of angles. Let's go ahead and name these 1 and 2. And I'm going to name these 3 and 4 up here. So we're going to focus on this part of the shape, and then the argument will work the same for all the other corners, so you can just duplicate it on your own. So what do we know about this shape? Well, if I can get these 2 triangles congruent, then I can get 1 and 2 congruent. I get 3 and 4 congruent. So if a rhombus is a parallelogram, it's got all the properties of a parallelogram. In particular, that means that the diagonals have to bisect each other, which means that these 2 pieces have to be congruent, right? That has to be the midpoint of AC, which makes let's call that M congruent to MC, right? So if we call that point M there, AM and MC are going to be congruent. But wait a second. If we have AM congruent to MC, right, and that's because the diagonals bisect each other in a parallelogram. Diagonals of a parallelogram bisect each other, right? What else do we know about these 2 triangles? Well, they share a side, don't they? So MB right there is in each of those triangles. So we have MB congruent to itself by reflexive. And from the very definition of the rhombus, don't we have AB congruent to BC? Right? So AB is congruent to BC because in a rhombus, all the sides are congruent. So what does that give us on these 2 triangles? We've already got side, 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 don't we? Triangle ABM is congruent to triangle, let's see, CBM by side, side, side. Okay, so that means that 3 and 4 are congruent because of corresponding parts of congruent triangles. The same is true of 1 and 2, right? Those are also corresponding parts of congruent triangles. So let's take those one at a time. So if angle 3 is congruent to angle 4 by CPCTC, then that means that the diagonal bisects that angle, right? If those two angles are congruent, then the diagonal is clearly bisecting the large angle at B. But there's some symmetry to this picture, right? The same argument that I made over here would have worked on these two triangles. We've also got a reflexive on DM. These two are side, side, side. And so that makes, if I call these, say, angle 5 and 6, those are congruent as well, right? So we've got DB bisecting both of the angles in the rhombus that it intercepts. So DB bisects its angles. Now, to get that AC bisects its angles, we could do the same argument, but just with these two triangles here, right? Look at these two. Aren't these also side, side, side congruent? You got these two pieces congruent to each other, DM and MB, for the same reason. M is the midpoint, it's a parallelogram, so it bisects each other. So we've got side, side, side on these two triangles, which makes those angles congruent and makes those angles congruent. Right? So both of the diagonals bisect the angles. But we're not done because we still need to prove that they're perpendicular to each other. So let's go back to 1 and 2. So if angle 1 is congruent to angle 2, also by CPCTC, in that first pair of triangles, right? Well, what else do I know about 1 and 2 besides the fact that they're congruent? 1 and 2 are also supplementary, aren't they? Those are linear pairs, they form a line, so they have to add up to 180. Well, if I've got two angles that are supplementary and are also congruent, then those angles have to be 90, don't they? So angle 1 and angle 2 are both right angles, which means that AC has to be perpendicular to DB, right? So the fact that the four sides are congruent in a rhombus allows us to do all of these triangles side, side, side congruent, which means that the diagonals are bisecting each of the angles in the rhombus, and it also means that the diagonals always have to be perpendicular to each other. So back to our quadrilateral family tree, we can tick both of those off as proven. Right? So we've proved the diagonals bisect the angles, we proved the diagonals are perpendicular. I won't prove that all sides are congruent because that again is the definition. And then to round out our family tree before we get into some numerical examples here, we have this last shape, which you probably recognize already, you know what I'm going to. That's going to be a square. So how do you get a square? Well, remember when we had the parallelogram and we said we want all the angles to be congruent, we got a rectangle? Or if we said all the sides to be congruent, we got a rhombus. Well, what if we asked for both of those? Right? So if you take a rhombus and you ask for all the angles to be congruent, then it's going to straighten that rhombus up, they'll all be right angles, and it'll end up being a square. If you take a rectangle and you ask for all the sides to be congruent, well then that rectangle is going to get squished or stretched, depending on how you want to think about it, and it'll end up a square. So a square is what you get by applying both of these properties to a parallelogram, or the other property to either a rectangle or a rhombus. And since a square is at the bottom of this family tree, think about what that means for the properties. Is a square a rhombus? Yes. So it has all the properties of a rhombus. It's also a parallelogram, so it has all the properties of a parallelogram. Right? Same thing between a square and a rectangle. A square is a special type of rectangle, which means it gets all the properties of a rectangle. And of course, a rectangle is a parallelogram, so it gets all of those properties. In other words, a square gets all of the properties that we've been talking about. Every single property we've proven for a parallelogram, a rectangle, or a rhombus all apply to a square. So if you want to be a quadrilateral, a square is actually a pretty good one to be because you get everything. So now what we're going to do is take these properties and apply them to some examples with numbers and it's a little bit of algebra. So we're going to jump right into rhombuses, rhombi I should say, because they're kind of the most interesting one to work with. Rectangles are sort of interesting. Rhombus are a little bit more interesting though. So if in a rhombus ABCD here, I've got some information about the shape. Now they haven't given me a picture, so I'm just going to draw one. I got ABCD. Whenever you label a quadrilateral, you have to go in one direction. So I can start anywhere I want with A, but once I pick a direction to go, I have to keep going in that direction. I can't skip around the shape. So you go either clockwise or you go counterclockwise. So they're telling me AB is 2x minus 2, and they're telling me that BC is x plus 8. So how am I going to solve for x here? Well, I can use the most basic property of a rhombus. All four of these sides have to be congruent, which means in particular 2x minus 2 has to equal x plus 8, and that's some simple algebra. I get x equals 10. And since they wanted BC, be careful, right? BC isn't 10, BC is 10 plus 8, or 18. Okay, so that's the answer to that one. BC is 18. Pretty straightforward application of a rhombus. Here's something a little bit more interesting. Here we have the diagonals of the rhombus being 10 and 24. So they're telling us that if I draw the two diagonals of the rhombus, that they're 10 and 24. Now, I don't want to do this. I don't want to come in here and say, okay, this is 10 and this is 24, because notice my picture just got real sloppy. It's hard to read now. There's kind of stuff all over the place. So instead, what I want to do is remember that in a rhombus, the diagonals always bisect each other. So if this is 10, then I could just say 5 and 5, right? Because that'll make 10. But now my picture is easier to read. And if this one is 24, I could just come in here and go 12 and 12. So now I've got the diagonals that are 10 and 24, just like the picture of the problem says. I'm supposed to find the length of one side. So let's go ahead and call that side x. How am I going to do that? So the first time you see this problem, it's actually a little bit tough to figure out. But if you remember the properties of a rhombus, one of them was that the diagonals are always perpendicular, which means that that is a right triangle. So if I pull that out for a second, right, I've got a triangle here with a leg that's 5, another leg that's 12, and an angle that's a right angle. That means I can use Pythagorean theorem to figure out what the hypotenuse is. Right? Remember, Pythagorean theorem says that a leg squared plus another leg squared is equal to the hypotenuse squared. That's 25 and 144 in this case, which is 169. And you might recognize that one. That's a perfect square. X is 13. So remember in the beginning of the year, I told you that right triangles pop up all over the place? Well, here they are again. You're in a rhombus, but you've actually got 4 right triangles here, and we can use that to find missing sides. Here's a variation on this problem. So this time we've got a rhombus, PQRS, and they're telling us that PR is 16. So again, I'm going to go in here, and I'm not going to label PR 16. I'm going to label PT8 and TR8. And then they tell me that QS is 30. Again, I won't label this whole thing 30. I'll instead call that 15 and call that 15. And they're asking me to find the perimeter of the rhombus. So just as before, I could find the length of any one side by using Pythagorean theorem on any one of these triangles. So if I do that, I get that x squared is equal to 8 squared plus 15 squared. And you can work that out, but you'll get x equals 17. That's a triple 8, 15, 17. But that's not the answer to the question, right? Because the question said the perimeter. So what is perimeter? Well, perimeter is all the sides, x plus x plus x plus x, right? Or just 4 x's. So that's going to be 4 times 17, or 68. Right? Oops, my whole screen just moved a little bit there. So if you know the length of the diagonals of a rhombus, you can find out the length of a side, or the entire perimeter, by using Pythagorean theorem. Very classic question about a rhombus. Let's take a look at another example here. So we've got a rhombus ABCD, again no picture, which means we're going to draw one. So ABCD. Notice when I draw my pictures, I don't worry too much about making it perfect. I just need it to be good enough to label and see what's going on. So angle A is 30 more than twice the measure of angle B. All right, let's break this down. Angle A is 30 more than twice the measure of angle B. So they're telling me about A in terms of B. That means that I'm going to make B x. And then how do I represent A? If it's 30 more than twice the measure of B, well, twice the measure of B would be 2x. 30 more than that would be plus 30. So there's my two angles, 2x plus 30 and x. I'm supposed to figure out what angle B is, which is to say what angle x is. What do I know about these two angles? Well, a rhombus is a parallelogram. And one of the properties of a parallelogram was that consecutive angles were supplementary. So I can come in here and say 2x plus 30 plus x equals 180. Right? That's 3x plus 30 equals 180, which means 3x is 150 and x is 50. Now they didn't ask me for x, they asked for angle B, but angle B is x, so that's the answer I'm looking for, right? Angle B is 50 degrees. So remember, because a rhombus is a parallelogram, we still get all of those properties, and we want to continue to use those. All right, a couple more angle examples, and we'll wrap this up. So here, they're telling me angle 2 is 5x minus 1, and SPQ, which is this big angle here, right? SPQ is 12x minus 24. So I have to think about what's the relationship between angle 2 and this big angle here. Well, what do I know about angle 2 and angle 1? Since this is a rhombus, the diagonal has to bisect the angles. That tells me that angle 1 and angle 2 are the same. So if 2 is 5x minus 1, then angle 1 is also 5x minus 1. Does that make sense? So what can I say here? Well, I can say 5x minus 1 times 2, right, has to equal this larger angle SPQ, and that's the 12x minus 24. So I get 10x minus 2 equals 12x minus 24. And solving for x, I get 2x is, 22, so x is 11. Is that the answer to my question? No, they wanted angle 2, right? So the measure of angle 2, that's 5x, which is 5 times 11 minus 1, so that's 55 minus 1, which is 54. Right, so that's the size of that angle. So we're going to stay in this picture, but we'll just change the setup a little bit. So what if they tell me angle 2 is 7x minus 6, and angle 3 is 11x minus 12? Now this one, 2 and 3 are not the same angle, right? These are totally different angles. There's no direct relationship there. But remember that the diagonals of a parallelogram are perpendicular. So that's got to be a right angle. Which means what has to be true about 2 and 3? Well, since they're in the same triangle as that right angle, they have to add up to 90, don't they? So I take 7x minus 6, I add the 11x minus 12, and that's got to be 90 degrees because that's how much is left over in this triangle. I've already got 90 there. I need another 90 to finish off the 180. 18x minus 18 equals 90, which means 18x is 108. And let's see, 6 I think will do it because 6 times 10 is 60, 6 times 8 is 48, so 6 times 18 is 108, that means x is 6. Is that the answer to the question? Yes, they want the value of x, so there we go, x equals 6. So angle 1 is 40, I'm just going to go ahead and put a 40 in there for angle 1, and they want angle 3. Alright, so we've got to move our way around this shape to get over to angle 3. So how could we do it? Well, maybe the first thing you might notice is that since it's a rhombus, we know the diagonals bisect each of the angles. So if angle 1 is 40, angle 2 has also got to be 40, right? So that gets me into the same triangle as angle 3, but I still have two unknown angles. Hopefully by now you recognize that that angle right there is a right angle because the diagonals are perpendicular. So we've got a 40 and a 90, making angle 3 50 degrees. Right, so that's a nice quick one there. And then one more with the same picture. This time angle 1 again is 40, right? But they want the measure of angle PQR. So we're looking for this entire angle here, right? PQR. Well, just as we figured out before, if angle 1 is 40, angle 2 is also 40. We know that we have a right angle there, which makes angle 3 50. But if angle 3 is 50, what's angle 4? That's right, it's got to be 50 as well. So those are both 50, meaning that angle PQR, right, that has to be 100. Now there was another way we could have figured that out also. Since a rhombus is a parallelogram, we know that the consecutive angles are supplementary. So if these two angles are both 40, that makes the large angle here 80 degrees. And if that large angle is 80, then the next large angle is going to have to be 100 to add up to 180. So I hope you found that helpful. If you have any questions, you can leave them in the description, or if you're in my class, just ask me next time you see me. If you enjoyed this video, please give it a like, subscribe to my channel, feel free to leave a comment below, and as always, have a great day.